Good morning. I'm Peter Bedini, a program manager in the space exploration sector. I've been at APL now for about 16 years. I'm going to talk about the Dragonfly mission concept, but first let me take a minute and give a little background. There are two types of NASA science missions. There are strategic missions where the work is assigned to a particular organization to implement, and then there are competed missions, which are those that are actually selected in an open competition. In planetary exploration, there are two primary programs of competed missions. There's the Discovery program, in which our APL's Messenger spacecraft was part of that. And then there's the larger New Frontiers program, the first mission of which was the New Horizons mission, also by APL. The two other New Frontiers missions that have been selected are the Juno mission, which is now circling Jupiter, and the OSIRIS-REx mission, which launched last September, and it's on its way to an asteroid from which it's going to return a sample to Earth. Dragonfly is being proposed by APL to be the fourth mission in the New Frontiers program, if they select us. Now, when you first hear the high concept of Dragonfly, it might seem a little ambitious or maybe even audacious, but I hope in the next several minutes, going through these slides, I'll expand on that concept and demonstrate that it's not just a very compelling concept, but that we have a viable formulation for it, and it's well worth NASA's investment. Dragonfly proposes to send a nuclear quadcopter to look for life on Saturn's moon, Titan. Seems kind of straightforward or arbitrary, but let's explain this and see that it isn't. First of all, let's talk about Titan, the target. Titan is the largest moon of Saturn. It's shown here along with its very small many neighbors. It is an ocean world. It's a designation for only a few places in the solar system which are thought to hold the ingredients for life. Others are the Europa, which is a moon of Jupiter, and also Enceladus, which is another moon here, a much smaller moon of Saturn. But unique about Titan is that it's got a liquid cycle very much like Earth's water cycle, but it's with methane. So it's a hydrocarbon version of our water cycle, and no other place in the solar system has that. Now, Titan is known to be very rich in complex organic materials, and we know that largely by the observations from Cassini. That mission has been flying for 12 years, studying the Saturn system and Titan as part of that. It also put a probe called Huygens down on the surface back in 2005. So we know a fair amount about Titan, but there's still a lot we don't know, and in particular, the composition of the surface remains largely unknown. Dragonfly proposes to characterize the habitability of the Titan environment. It's going to investigate how far prebiotic chemistry has progressed on it, and it's going to look for chemical signatures indicative of water or hydrocarbon-based life. So we're not exactly looking for five-legged creatures running around or something like that, although if we did confront one of those, we'd be sure to take a selfie and send it home. The four measurements that Dragonfly will make to accomplish those objectives are here. Mass spectrometry will show us the composition of the surface and of the atmosphere. Gamma ray spectroscopy will tell us the elemental composition below the surface. We have a meteorology and geophysics sensor package, which will tell us about the atmospheric conditions, and also using a little geophone, it might tell us whether there's seismic activity on Titan or not. And of course, there's a camera suite, which gives us context for the in situ measurements. It helps us find our next landing site when we're flying, and also characterizes the geologic nature of the surface. Because this is a competition, I didn't want to put our actual images on here, so these are representative. Like, we don't have brownie cameras on Dragonfly. Now, we could take a lander and we could plop it down on Titan, and we could take these four measurements at one place, and we would significantly increase our understanding of Titan and its similar moons, or bodies like it in other ocean worlds. However, we can multiply the value of this mission if we add aerial mobility. because now we can look at this very diverse surface that is Titan. It's got a variety of geologic settings. Instead of just measuring in one place, we can go to many places and increase the science return substantially by moving around. Now, rovers do offer mobility, but it's much more limited. And it's also subjected to the trafficability of the surface. You can get an obstacle that'll stop a rover. If you have aerial flight, you can go over or around an obstacle. You also increase the range hugely by having an aerial mobility instead of just a rover. And in particular, in just a few flights, Dragonfly will be able to go farther than the Opportunity rover on Mars has in the last 12 years. So it's really a different paradigm. The image on the bottom here is from Cassini data. It's a projection of Titan, and you can see in the middle area here, there is this dark area that is smooth sands. The brighter areas away from that are perhaps more challenging landscapes or different geologic settings. So our approach here is to land in the interdune flats in this black smooth sand area, and then we can navigate with different hops to more interesting or diverse places to take measurements. So let me stop here for a second. We know that we want to go to Titan. We know that looking for life there is of supreme importance to the science community. We know what questions we want to answer. We know what measurements we need to take to answer those questions. And we have a plan to do this in many, many different spots to characterize Titan in a more broad way than just doing like a single pathfinder. But what makes this the real clincher for this concept and what makes it really a viable formulation is this. It turns out that the easiest place in the solar system to fly a quadcopter is on Titan. That's because Titan's got an atmosphere more than 4 times as dense as Earth's, and the gravity is only 1/7 that of Earth. So a human on Titan could put on some wings, flap arms, and actually fly. As a matter of fact, if this guy had been doing this on Titan instead of on Earth, he would have had a much better go of it. Yeah. This is a plot of a couple very important parameters for aerodynamic flight, and it shows that Dragonfly, which is this Titan Explorer here in the blue, is in a very comfortable range in the flight regime. It's actually near ultralight aircraft, wind turbines. It's very understandable. The characteristics of flight in that environment by a quadcopter are quite understandable. A quadcopter is actually quite straightforward. There's no gearbox like in a helicopter. It's straight drive, direct drive motors. There's been a drone revolution of sorts in the last dozen years, and they're everywhere, and the flight control algorithms and the flight characteristics are very, very well understood. We're using an X8 configuration. That's this double rotor on 4 different arms. That's for redundancy primarily. We can lose a couple of these rotors depending on which they are, and the mission keeps on going. We show here the high gain antenna in its stowed position. Once we get onto the surface, we'll deploy that, and it's got a 2-axis gimbal. We'll be communicating directly from the rotorcraft to Earth. We do not need an asset flying around Titan to help with that. In the left is the launch configuration. The top part is a heat shield. That'll keep it from burning up when it enters Titan's atmosphere. There's a back shell on the bottom where the thing is tucked in, and then the very bottom on the left picture here is the cruise stage, mostly a propulsion system that helps get us to Titan. I'll show you more about that in a minute. Now, Saturn is really far away, so it's simply impractical to propose that the power for this system would come from solar arrays. You've seen the big solar arrays on spacecraft at Jupiter and closer in. It makes perfect sense to do that, but when you get out of Saturn, these arrays would have to be so large or maybe use a new technology or both. Luckily, NASA has made available what they call MMRTGs. That stands for multi-mission radioisotope thermoelectric generators. RTGs have been used in space missions for decades. This is a small version of an RTG, and one just like this is powering the Curiosity rover that's on Mars now. A bigger one of these, an older type, is actually powering the New Horizons spacecraft now as it passed Pluto and is going to its next target. They put out constant power, but a lot of waste heat, so we're taking advantage of some of that waste heat and directing that into the body of the craft so that we can keep the electronics running at a cozy room temperature which saves a lot of work and don't have to worry about the electronics running in a cold environment. Also, the power coming from the RTG simply charges our battery, and then we actually operate off of the battery. It takes a long time to get to Titan, especially now that Jupiter is not in a friendly place to use as a gravity boost. It'll take a little longer. But we have pertinent recent experience with very long cruise phases with the New Horizons mission, and we're going to leverage that experience, especially with using hibernation modes and with low-cost operations. This is a schematic of the entry into the Titan environment. You see on the top left, the cruise stage is still attached to the capsule. That gets jettisoned, a drogue chute comes out, slows things down, then it pulls out a main chute. You can see the heat shield then being dropped off in the middle. While we're still descending, and by the way, this is not a fast descent. It's not like the minutes on Mars or on Earth. This is actually going to be more than an hour. It's a leisurely float down because of the thick atmosphere. We actually, while we're still on the parachute, we will turn on the sensors we have for landing. It's a robust set of redundant sensors, including LiDAR, radar, and cameras. And then we will power up, separate the back shell, and actually land on our own power. Now, this is the most challenging part of the mission, only because we have the least to say about where precisely we land here than we will later. Later on, we'll have the luxury of going out, doing a little survey and reconnaissance, picking a place, and then sequencing to go right there. This one, we're doing the best we can to pick a hospitable place in the smooth sands, and we're coming down, and we do have some control at the end there with our own power to move in case there's some big obstacle, like a big tree or something like that, that we need to miss. But of course, if we hit a tree, we win. So we come down, and this is a schematic of this inter-dune flats area. And it just shows, again, coming down with the back shell and then landing on its own. Once we've landed, we deploy the antenna. As I said, we'll be communicating directly with Earth, so there's no need for a orbiting relay asset. And one Titan day is about 16 Earth days, which means that with our baseline plan of flying once per Titan day, we have ample time to take our measurements, send it back to Earth, charge up the battery, take another flight. We have time in between the flights to get the sequence right after we pick a location and send it up. So it's not a very hurried cadence, and it's because we have this constant power from the RTG that'll last. If that power decays, all it means is we take a little longer to charge the battery. Here we'll pick up and go off again to another landing site. Now our partners on this, we have many partners, but the Penn State University Center of Excellence for Vertical Lift, they're one of 3 in the country, built this half-scale model for us. This is the first autonomous flight. It's a milestone of sorts. It's a completely programmed sequence, just like we will do on Titan. The only difference is this, it's told to find a couple different GPS waypoints and then come back and land where it took off. So you'll see here that it is up, it's going. This test bed, if we are selected to go forward, we will use extensively to develop the algorithm for flight and for landing. We'll develop it a little more and add some of the landing sensors that we need to put in to test that interface. And as we go further into the mission, we will develop a full-scale test bed to a model to fly around. To as great a degree as we can, we want to test as we fly, so we'll be using this to do some cold temperature operation, and we will change the algorithms and test faults and things like that. By the way, these rotors are actually constantly spinning, but there's this resonance with the frames per second that makes it look like a strobe here. I assure you they are spinning constantly. And here it is coming back down in front of the big red harvester or whatever that is that it took off from. Now the folks at Penn State have also rigged this thing up to look more like the drawings I was showing you that we expect the thing to look like, a little less aerodynamic than this. They put a cylinder in the back for the RTG and they put a box around it, and this is just another sample of it taking off in slow motion. I assure you that the flight unit on Titan will not have tennis balls for landing gear, but for right now that's just very practical. So that is the Dragonfly concept explained. I hope you agree that it is compelling, and I think it is quite viable and feasible, and we hope that NASA agrees and is willing to take a chance on us. Thank you very much.